Two events are independent if the outcome of any one trial does not affect the outcome of the other trials. In other words, knowledge about one event tells us nothing about the other, or the information in event A is completely irrelevant to the information in event B. For example, a couple has a baby girl. What's the sex of the next child? Well, knowing they had a baby girl is irrelevant to what the sex of the next child will be. It provided no additional information. These are independent events. The event of getting a 6 the first time a die is rolled, and the event of getting a 6 the second time a die is rolled. Knowing what happened on the first roll doesn't affect what's going to happen on the second roll. Two cards are drawn with replacement from a deck of cards. So the event of drawing a red card on the first trial, putting the card back in the deck, and then drawing a red card on the second trial are independent. For dependent events, the result of one event is affected by the result of another event. So for example, the event of getting a 6 the first time a die is rolled, and the event that the sum of the numbers seen on the first and second trials is 8 are dependent. Because to get a 6, so if you get a 6 the first time the die is rolled, that means your second roll you could get a 1, you could get a 2, or you could get a 6. So knowing that you got a 6 on the first roll and then trying to find, well, what's the chances of rolling a second time and getting a sum of 8, there's only one case where that could happen. Knowing that you rolled a 6 on the first roll. So this affects the probability that you'll sum to 8. They're dependent events. Two cards are drawn without replacement from a deck of cards. So let's think about a deck of cards. If you get a red on the first trial, there's 52 cards in a deck, and out of those 52, 26 of them are going to be red. But if you're drawing without replacement, then the next time you try and get a red card, there's only 25 red cards left in that deck. And 52 has changed also. You took away one of them. There's only 51 cards. So you've changed the probability. It's dependent. The intersection of two events, A and B, is the overlap of the two events that are in both A and B. That's your key word. So probability of A and B. That's the probability of A intersected with B. For mutually exclusive events, if we come in and draw a diagram, it should be pretty obvious that anything in A cannot be in B. It's impossible to be in both at the same time. If a student passes the test, what's the probability failed? It can't happen. It's impossible. It occurs with probability 0. A Paradisus rule. What's the probability of rolling a sum of 9? And the only ways to add to 9 are like this. So the chances of rolling a 9, you need this combo. And to roll a double, none of these are doubles. You can't have both at the same time. So this is an impossible event. It occurs with probability 0. Therefore, for mutually exclusive events, we can say this rule. For mutually exclusive events, the probability of A intersected with B will always be 0. Now, if you have independent events or general events, you have a picture that could look like this. There is a chance of an overlap when you're looking at A and B within your sample space. So for independent events, the probability of A intersected with B is the probability of A times the probability of B. This is also known as multiplication rule. So for example, find the probability that 4 randomly selected ropers are all missing one or more fingers. Let's break this problem down. Let's first find the probability that just one, not 4, just one roper is missing one or more fingers. So I'm looking for the probability of M. That's 12 headers plus 23 heelers for a total of 35 ropers out of the 256 that are missing one or more fingers. I'm now looking for the probability, instead of just one of them, that 4 of these ropers are missing one or more fingers. So that's the probability that my first roper is missing one or more, and that my second roper and my third roper and my fourth roper. Because these are independent events, we can come in and multiply these probabilities. So everywhere that there used to be an intersection, I've now replaced it with a times. I am multiplying these probabilities. Well, the chances of any particular roper missing a finger are going to be exactly the same. There's no reason roper 1 and roper 2 should have different probabilities here. So you could really see the problem as saying this. Change them all to roper 1. There's no difference between them. So I have the probability of a roper having a missing finger written out 4 times, which is the same as that probability raised to the 4th power. So if I plug in the value for this, the probability of a roper missing a finger, and raise it to the 4th power, that will give me back my answer, 0.00035. Because this number is so small, the chances of this are very unusual. This is an unlikely event. The future is uncertain and full of risk. Risk is the chance that an undesirable event will occur, but risk is also opportunity. That's where we come in. We are the leading professionals in finding ways to manage risk. It takes a combination of strong analytic skills, business knowledge, and understanding of human behavior to manage today's complex risks facing our society. Actuaries usually focus their work on either casualty, life and health, or pension jobs. This graph shows the average salary for actuaries. Our next example will deal with a problem from a casualty setting for actuarial science. If the independent probabilities that 3 people, A, B, and C, will be alive in 30 years' time are 0.4, 0.3, and 0.2 respectively, we want to find the probability that in 30 years' time, none of these 3 people will be alive. If they're not alive, that's 1 minus the probability that they are. So let's come in on a case by case. The probability that person A dies, that they're not alive, is 0.6. The probability that person B dies is 1 minus 0.3, 0.7. And the probability that person C dies is 1 minus 0.2, 0.8. So if I'm looking for the probability that none of these 3 people will be alive, I want to find the probability that person A is not alive, and person B is not alive, and person C is not alive. Now, the key to solving this problem is to recognize that people are always independent of one another as long as they're randomly selected. So knowing that person A lives or dies won't tell us whether or not person B lives or dies. That means we can multiply these probabilities. Anywhere that there's an intersection, you can change it to a times. And now if we plug in our numbers, the probability of A complement is 0.6. The probability of B complement is 0.7. And the probability of C complement is 0.8. So the answer to this problem is 0.336. In part B, we want to find the probability that only one person will be alive. Well, in terms of notation, this is the probability that A lives. But if A lives, that means that B and C both have to die. Now, if this does not happen, or the other thing that could end up happening, and I'm going to have to drop down a line here, the other thing that could have happened is that person B lived. But since only one person can live, that means that A has to die and C has to die. And if this doesn't happen, or the last scenario would be that person C lives. But if C lives, then A and B have to die. So this is the probability I'm looking for. To apply our rules, we'll switch unions to pluses. The next rule we'll apply is that intersections switch to multiplications. So I switched the first line to multiplication. I'm now going to switch the second line to multiplication. And then switching the third line to multiplication. So we now have the formula in such a way that we can go through and plug in numbers. The probability of A is 0.4. The probability of B complement is 0.7, and the probability of C complement is 0.8. Plus, when we come down to the next line, the probability of A complement is 0.6, the probability of B is 0.3, and the probability of C complement is 0.8. Plus, dropping to the next line, the probability of A complement is 0.6, the probability of B complement is 0.7, and the probability of C is 0.2. So if we add up these numbers plus these numbers plus these numbers, we'll get back the probability that only one person alive is 0.452. To find the probability that at least one person will be alive, let's look at a number line. The potential outcomes are that no one is alive, all three people died. Or one person lived and two people died. Or two people lived and one person died, or all three people live. This is our sample space. So if I'm finding the probability at least one is alive, that means one person could have lived, or two people, or three people. Now, finding the probability that one person lives is what we did on part B, and I think we all can agree that was a lot of work, and we don't want to have to repeat that for 2 and 3. So the other option would be to think in terms of a complement. I could say, well, I'll find the probability that no one lives. And if I find the probability that no one lives and do this entire thing, 1 minus that probability, it should sum to the probability I'm looking for, right? Because probabilities always sum to 1. So if I do 1 minus the probability that no one lives, that's the same as finding the probability that one person or two people or three people live. Now we already found the probability that no one lives in part A. That was 0.336. So the probability of at least one being alive is 0.664. These are the works cited for this lecture.